Part J, Trig Identities. In pre-calc, you learned a whole bunch of different trig identities. We're just going to focus on a few of those, in particular the ones that are going to be useful for us for solving some trig equations. I first want to look at some negative angle identities. And to understand these, let me draw a small picture over here. If I have the angle theta that looks like that, the angle negative theta will be spun the same amount, just in the negative direction. If I want to figure out the sine of negative theta, remember that the sine is our y-coordinate. I think both of these angles will have the same y-coordinates. One will just be positive and one will be negative. That means that the sine of negative theta has to equal the negative of the sine of positive theta. The cosine of negative theta, remember, is our x-coordinate, and this time they have exactly the same x-coordinate. Positive over here, positive over there. The cosine of negative theta should equal just the cosine of regular theta. To figure out the tangent of negative theta, well, rather than trying to use that circle over there, I can just do the sine of negative theta divided by the cosine of negative theta. So this is negative sine theta divided by cosine theta, and you're going to get the negative of the tangent of theta. The sine of negative theta is the negative of the sine of regular theta. The cosine of negative theta just equals the cosine of regular theta, and the tangent of negative theta equals negative the tangent of theta. Our second group of identities, are the Pythagorean identities. The first one, and definitely one of the most important trig identities, says the sine squared of theta plus the cosine squared of theta equals 1. This just comes from using what we know about the unit circle. Any point has coordinates cosine theta, comma sine theta, and remember that our radius is 1. So for any triangle that we draw in, our radius is 1, our height of the triangle is the sine of theta, and the base of our triangle is the cosine of theta. This is just the Pythagorean theorem. Sine squared theta plus cosine squared theta has to equal 1 squared. To get our next Pythagorean identity, what I'm going to do is take my original one and just divide everything by the sine squared of theta. So I'm going to take my sine squared theta plus cosine squared theta equals 1, and I'm going to divide all the pieces by sine squared theta. That gives me 1 plus cotangent squared theta equals cosecant squared theta. I can create a third Pythagorean identity by taking my original sine squared theta plus cosine squared theta equals 1 and dividing all the terms by the cosine squared of theta. This will give me the tangent squared of theta plus 1 equals the secant squared of theta. So the three Pythagorean identities are sine squared theta plus cosine squared theta equals 1, 1 plus cotangent squared theta equals cosecant squared theta, and tangent squared theta plus 1 equals secant squared theta. Finally, we have our double angle formulas. First, we have the sine of 2 theta equals 2 sine theta cosine theta. The cosine of 2 theta equals cosine squared theta minus sine squared theta. But actually, there are two other ways we can write that one as well that go back to our Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Another way we can write this, just in terms of sines, is realizing that from our Pythagorean identity, the cosine squared of theta just equals 1 minus the sine squared of theta. This will equal 1 minus sine squared theta minus sine squared theta. Drop the parentheses and combine like terms, giving me a second version of this as 1 minus 2 sine squared theta. We can now do the same by replacing the sine squared theta in the original with 1 minus cosine squared theta. So cosine squared theta minus 1 minus cosine squared theta. You'll go and distribute your negative. And our other version is 2 cosine squared theta minus 1. The cosine of 2 theta equals all three of these versions. This is the original one, but we're going to see more often it'll be useful to use one that either just involves sines or just involves cosines. So now that we have these identities, let's see how we can use them to solve some trig equations. First example, let's look at the cosine of 2 theta minus the cosine of theta equals 0. Dealing with these again between 0 and 2 pi. Well, I can replace this cosine of 2 theta with one of my cosine double angle formulas. Since I already have a cosine in my problem, I'd rather replace this with the one that just uses cosines rather than one involving sines, because then I'll just have one trig function in my equation. This gives me 2 cosine squared theta minus 1 minus the cosine of theta equals 0. So 2 cosine squared theta minus cosine theta minus 1 equals 0. To factor this, I'm going to factor this into 2 cosine theta and then cosine theta with something. I think I need a minus 1 over here and a plus 1 over here, because negative 2 cosine theta plus 1 cosine theta gives you negative cosine theta. Setting both parts equal to 0, we get the cosine of theta equals negative 1/2, and the cosine of theta equals positive 1. So theta is going to equal 2 pi over 3 and 4 pi over 3. And then from this part, you're also going to get 0. Cosine squared theta plus sine theta plus 1 equals 0. Well, I can use my Pythagorean identity here. Cosine squared theta, I know from my Pythagorean identity, rewriting that a little bit, that can equal 1 minus sine squared theta. So I can say 1 minus sine squared theta plus sine theta plus 1 equals 0. So negative sine squared theta plus sine theta plus 2 equals 0. I'm going to factor out a negative 1 before I do any more factoring with this. So negative 1 times sine squared theta minus sine theta minus 2 equals 0. And factoring this quadratic, I get sine theta and sine theta minus 2 over here plus 1 over here. And setting the parts equal to 0, I get the sine of theta equals either negative 1 or the sine of theta equals 2. Well, sine theta equals negative 1 when you're at 3 pi over 2. And sine theta equals 2, actually that's not going to happen. This part of the equation will give us no solution. But that's okay, we still got one solution from the other part. There's only one solution to this equation, and it's 3 pi over 2.